So, welcome to episode 101 of Quarkus Insights, where we'll have a 101 on Loom, or virtual threads, as we should call it. And I think all of you have been here in some form, Clement and Arthur and Holly. And whoops. And yeah, so you can introduce yourself when you speak the first time. But basically, we want to give an overview about Loom or virtual threads and how it affects not affects, what's called, mixes in with Quarkus. And I even think Clement might or Arthur will talk about some of the challenges there are on this. As always, there's a chat. You can post questions, and we'll kind of merge them into the conversation. And otherwise, I'll give the word to Arthur, I think, to give it and get started.
Hi everyone, thank you very much for the invite here on Quarkus Insight. Indeed, so with Clement, we've worked on, and the rest of the Quarkus team, mainly with Clement, we've worked on integrating virtual threads, the new feature of Java 19 to Quarkus in order to benefit from some of the abstraction they give us in terms of imperative programming while retaining the performance of reactive programming. So I guess this presentation is pretty much about being able to distinguish the old reactive model using vertex neti and using reactive strings and this kind of asynchronous programming, and the new paradigm you are in with mixing virtual threads and the reactive engine of Quarkus, while also studying, how those interactions between the reactive model and the virtual thread, engine in the new JVM might cause any problems or performance issues with Quarkus specifically. If Clement wants to add something, maybe.
No, yeah, that's exactly it. So I have been following the progress around the Loom project, and so the addition of virtual threads inside the JDK since mostly the beginning of the work. And for us, the challenge and is how is this going to change how we do things in a modern framework like Quarkus? Because of course you can use virtual thread on your standalone Java application, but today most Java applications that are running are actually part of user framework. It can be Spring, Gelidon, or Quarkus, or Micronaut, whatever. So at some point you need to ask yourself how this framework will utilize this virtual thread. What does that change? What does that change for the framework, for the users? What we can do with them that we were not able to do that? What about the performance, the concurrency? And the last question, what about the cloud? How does it behave when we're running our application in a container with half a CPU? Because that's what we get on the lucky days. So we get half a CPU and we're really, really happy. So that's all the questions that we had, and but at some point we needed to start somewhere. So Arthur started working on that as part of his PhD, because Arthur didn't say it, but he's a PhD student, and we started looking at various approaches that we are going to detail later. What works, what doesn't work, the maturity of the Java ecosystems, and things like that. So I think now we can go ahead and Arthur, maybe you can try to explain what's the difference between a virtual thread and a not so virtual thread.
Yes, thank you. So this is an old presentation we gave at Devox France, so it was in French. Now we're going to do it in English. I think the first thing we need to do is to come back on the idea of what a thread is, and this is basically just to be on the same basis. It's going to take a minute or so. It's basically a unit of concurrency, right? And unlike a process, threads are going to share a certain amount of state, whereas processes do not, and they're going to have their individual stack that is split. And the problem with the current implementation of the Java threading paradigm is that your Java threads, the traditional ones we call platform threads, are actually in a one-one relationship with the abstraction, the thread abstraction of your operating system, which means that when you create a thread on Java and you're running on Linux, for instance, you're going to perform a call to the pthread library, that it's going to create a thread in Linux that is basically, I think, a task struct internally. And so these entities at the operating system level are so general that they have a tendency to be quite heavy in terms of memory consumption. So I think the stack is 1 megabyte by default when you create a Java thread that is going to create a pthread under the hood. And also the time it takes, to swap threads onto a CPU core. So you need to offload the context of the first one and then load the context of the new thread. So those kind of operation takes time. So it's additional latency when you want to, when in case of web server, for instance, and the memory consumption. So those are the two things, latency and memory consumption, that virtual threads are supposed to alleviate by introducing, threads managed by the JVM. So this is the imperative model, right? The old one. Clement, if at some point you want to, intervene.
No, you go ahead. Go ahead.
Okay.
You're good.
So please feel free to correct me if I'm wrong or something. So this is the old model, right? This is the imperative one. You have your workers, you have your request incoming, and as soon as you receive a request, you're going to offload the handling of this request to a worker thread. And as you can see in this model, when you need to perform input-output on you, as you're handling. So for instance, you receive a request, you need to perform some database fetching to send the result back to the client. Your worker thread is going to be blocked. What it means is that the operating system is going to take it, put it in a waiting queue, and put a new worker thread in its place. And the problem with that is that you will have tens or even hundreds of worker threads that are going to be waiting in memory, doing nothing else than just taking space in your memory at a given time, if you have many input-output in your server. And the time it takes to swap them off and swap it back on is going to take time too. Hence the reactive model, where you are going to limit the number of threads you're going to use, and you are going to try to multiplex the number of concurrent operations you can do on one only thread. This is the event loop model. So basically what's going to happen is that you will have your first request that is going to come in, the blue one. You're going to process it, and as soon as you need to perform input-output, you're going to basically schedule a continuation. That is to say, what do I have to do once the operation is complete? And then you're going to just start processing another request. And so to do this, Quarkus uses native vertex that itself uses non-blocking syscalls in order to be able to, the task is doing something with the drivers of your peripherals and stuff, the devices. And as soon as it's complete, your operating system will tell your JVM, hey, it's done. Maybe you can do something else. And the event loop is going to pick it up and be able to schedule it back on in its queue. So the idea is really to multiplex several requests on the same thread in order to avoid taking too much space in memory and having this, swapping them on and off, taking time actually. And so once we've said it, since we have a limited number of event loops of threads that are going to run our requests, we must not block them. If you block a worker thread, since you have hundreds of them, it's not really a problem, right? It's going to be blocked and then it's going to come back in the pool. Since you have only a limited amount of event loops, by default, it's twice the number of CPU cores in Quarkus and Vertex, I think. Let's say you have one CPU core that makes 2 event loops. If you block one event loop for too long, you are basically losing half your computing power in your server. So as soon as you start block, yeah.
So about that, so first remember these rules, because we will come back to that later. The rules about 2 times the number of CPU cores has changed in Quarkus very, very recently. So now it's only 1 per CPU core. After the newest performance benchmark we did, we realized that it was not worth the cost. So we are back to 1.
Yeah, so as Clement told you, that's really a golden rule. We must really respect it. So if you run 1 CPU now, you're losing 100% of your computation power if you block your loop.
So just for people who might not, like, if you're doing reactive and you're following rule, do not block the IO thread. What if I need to do some computation? Like run over fold about 1,000 times.
That's a very good question, and actually we should go back to that one later, but I will do a quick answer here. If you are doing CPU intensive tasks, so computation, don't do that on an IO thread, because your IO thread is here to be very, very fast, to just pick an event, do something, boom, done. Pick an event, do something, done. If you want to block, then offload that to a worker thread. That's not because we are a reactive framework that we can't do that. And actually, most of you don't see it, but when you have a blocking endpoint using Quarkus, it's what is happening behind the scene. We say, oh, maybe you are going to block for CPU intensive or any reason, we offload to a workers thread. And that's fine. That's fine.
Yep.
So just to summarize the points. Oh, sorry. Did someone?
No, go ahead, Arthur. Go ahead.
Sorry. Just to summarize what we've told this far, we are going to compare quickly, the imperative model and the reactive one. And basically, the advantage of the imperative model is it's simple development model. Since everything is synchronous and blocking, you just have to start a task, and then as soon as the task completes, your code is going to jump to the next line, and you get this abstraction, this very powerful abstraction of imperative programming. Its cons, as we've seen, is that it's quite expensive memory-wise, and you can limit the concurrency because you can't have, millions of platform threads on a server, especially if you don't have that much memory available on the server. Now, reactive programming, on the other hand, will have a more complex development model. So as we've seen, as soon as you start an asynchronous operation, you need to somehow tell the computer that you want to then, as soon as it's complete, execute a continuation. So basically, that is going to, translate in terms of callbacks and promises or async await in your code. And those are things that are going to transpire from, one function to another in order to be able to pass this asynchronous behavior along the way. This is something, if you're interested in this kind of stuff, you can check out the colored function problem. It's basically, as soon as you start, in case you are using async await paradigm, you will have to start putting async await everywhere, and then your entire code is going to be polluted. So this is something that Loom is actually alleviating, right? You don't have any difference between the imperative and the reactive code now. So it's really taking the best of both worlds and putting them together. So that's pretty much what said. And the way they do it is that they are going to introduce this new construct that we call virtual threads. That is going to be a thread that is managed by the JVM, and that won't appear as a thread for the operating system, right? So as we've said, if you create a Java thread, your operating system will see that you've created one thread because it's actually an operating system instance that is going to be tied with it. Data structure in the operating system that is going to have a thread. Now, if you use virtual threads, you are not creating threads from your operating system. You are just going to create Java data structures that are going to be mounted and unmounted from actual platform threads. So you can have tens or hundreds of virtual threads that are going to be mounted and unmounted on and from one only carrier thread. That is, the good old platform Java platform thread. And the way it's going to work is that your virtual thread is going to mount itself on the carrier thread, so your good old Java thread. And as soon as it's going to need to perform a blocking operation, the JDK has been rewritten in order to enter a method. So the virtual thread is going to enter a certain method when it needs to block. That is going to unmount it from the carrier thread, hence leaving room for another virtual thread to come in and to mount itself on it. And as soon as its operation is complete, then it's going to reschedule itself in the carrier work queue in order to be able to do work again.
So before going further, I just want to add a few things about that. So the oldest among us, probably Max, did see this very, very early in your career, Max, because that's what we call green thread in Java 1 and pre-Java 1.
It's good.
So, yeah, well,
slow stuff.
Yeah, not sure it was that good, but if they switched, it had a reason. So it's actually very similar to what Green Thread were doing at the beginning of Java. The big advantage here is that now we have the choice. You decide if you want a regular process thread or OS threads, or if you want to have a virtual thread. So you have that choice. Before it was Green Thread for everything and then OS thread for everything. And finally now we can choose between both. And one thing is important too is that in terms of data structure in the JVM as a users, for you it's just a thread. It's a Java long thread. So it can be virtual or processed, it's just a thread. So you will play with runnable and things like that, it's just plain thread. So the only difference is that now you have a isVirtual method, so you can check if it's a virtual thread or not.
And just to piggyback on what Clement, I think I wasn't born when Green Thread was still a thing in the Java ecosystem, but I think you only had one actual platform thread to support them all, right? You couldn't have like 2 different threads that were going to multiplex your green threads. It was only one. Now with Loom, one new thing too is that you can have actually multiple carrier threads. So you can basically dispatch your virtual threads, your tens or hundreds or millions of virtual threads among several platform threads. And so they do it by implementing a work stealing algorithm, which is something that actually fits well with the kind of workloads you get when you want to do a web server, typically. And this is something that the Go network scheduler had a lot of research about. I think by 2007 or 2008, there were several papers that were published saying we compared the performance of work stealing, and without work stealing seems to really enhance the performance of a typical web server application. So this is something they implement. So the thing is that you have several carrier threads that are going to be used to dispatch your thousands of virtual threads. And if one carrier really has too little to do, it's going to be able to take work from another carrier thread that has too much to do. This is pretty much what we represented here. So it's both a very good thing, so it's going to enhance your performance, but it can be also quite tricky to use because your virtual threads are not bound to a platform thread, which means that the most obvious thing we could think of is the thread local abstraction, right? In Vertex, basically, you had those verticals, which are data structures that are going to be bound to a single thread. So what you can assume is that if you store some data in a thread local, it's always going to be available because you are always going to be resumed on the same thread. It's not the case with virtual threads anymore. First, thread locals are not usable. It's completely another thing, but you can't make the assumption that your virtual thread is always going to be resumed on the same carrier thread. This is very important.
Yeah, and this is for me the one that it took me a while to get. This was that these events. Oh, sorry. What are they called? Task threads. They run on basically one. Well, most likely to be on the same thread, but when you get on a load, it will swap over to somewhere else, and then you can't rely on thread locals, which is something that is relied on a lot of places in existing Java code. Completely. And that's where our trouble starts or begins, so we can call it.
Yeah, you don't want to be the one debugging those.
Yeah. You can't debug it.
You can't. And this is, and I want to make sure that people hear this. Like, I think we all want, like, the Loom program model is good. Like, this is a much more understandable, debuggable thing. But where things become interesting, challenging, and that's where we're trying to find a way. How do we get there? There's a lot of code in and outside. Well, not in Quarkus anymore because we just fixed it. But in other frameworks, there are just a lot of thread local usage, and even in users' own code. And the problem is you don't see it. Like, you can't. It's just a variable you access, and now suddenly it's gone because you got swept over to another thread and you didn't realize it. So that's the thing that looms in Loom is that part. But the program model is great, and Anyway, go ahead, Arthur.
And don't worry, we are going to see the development model very, very soon, but we wanted to explain how things works, because from that you will understand what we can do and what we can't do.
Yeah.
And this question of thread local is very important, and it causes a lot of headaches, regarding the interactions between Netty and Quarkus Loom, Quarkus virtual threads, because Netty has a heavy use of thread locals, since its main hypothesis is that you're going to have a restricted number of event loops, those Netty event loops. So it uses a lot of thread locals. They even have their own implementation that is called fast thread local, that does a bunch of stuff with buffers and everything. Don't really understand what's going on, but we had many problems with that performance-wise, because the thing is, if you have, let's say, 2 instances of thread locals, that's okay. If you have 1,000 instances of thread locals because you are using 1,000 virtual threads, then all of a sudden your application is out of memory and it gets killed by your operating system, which is something that might not be really good in production. So just to compare the reactive and the Loom virtual thread model, we can already see some things that look quite alike. So your carrier thread is basically your replacement for your event loop in a reactive model, in the sense that it is a single thread on which are going to be mounted and unmounted the processing of tasks. Now, the difference is that in an event loop, the tasks you are going to run upon the event loop have to execute from beginning to end. And then you are going to submit callbacks in order to execute something that must be executed after the completion of an IO operation, hence the complicated programming model. With the carrier thread and the virtual threads, your virtual thread, as we've seen, it's basically the virtual thread 1, 2, 3. You can basically suspend the execution and then resume it, and it's going to start where it basically stopped before yielding control back to the event loop. So although there are similarities, it's very different in this sense that you can actually take them back and put them back on, and they are going to be able to resume where they stopped. Whereas the tasks on an event loop need to be executed from beginning to end, and then you have to use some continuation passing style in order to submit a callback or submit a promise or something in order to continue the computation later on. So this is basically saying it a bit in a different way. Clement, I don't know if we should take time to explain this.
No, I think you can pass it. We will share the slides if you want to go more into details in how things works. But no, we can go ahead and look at some code, because it's time to see some code.
Maybe I'll share my IntelliJ screen afterwards, just a collection on how we actually implemented virtual thread support in Quarkus. So you have the same endpoint 3 times. So it's supposed to do the same thing, but with different development models. So on the left-hand side, you have your old imperative blocking model, right? So you basically have a path. It's a REST API, right? So nothing fancy here. You just create a list that's going to fetch everything in a repo. Then you're going to pick one element and return it. So as you can see, it's very much one action, then you return it. Imperative blocking, easy. Now, on the right-hand side, you have a reactive non-blocking. So what you do is that you're not going to return just a fortune. You're going to return a uni to a fortune, which is basically a promise, a placeholder that says sometimes in the future you're going to receive some data, but for now I'm just giving you a uni. And so as you can see, the programming model is a bit different and a bit more elaborate. It's a very simple example, so it's still a 2-liners, but when you have more complex logic and concurrent and asynchronous logic, it can get very hairy and very hard to understand, whereas the blocking paradigm will remain fairly simple, right? It's just going from one line to the next. So as you can see, this is a very much declarative functional programming when you have chain operators. It's a reactive string, actually. And so you need to be fluent in this paradigm declarative functional stuff. Now on the middle, you have your Loom with Quarkus with virtual threads. And the only difference is that you need to add this little annotation that is @run on virtual thread. And so the thing is that you need to consider your endpoint as being a blocking endpoint, but instead of offloading the computation on a traditional thread, you're going to offload the computation on a virtual thread. So it really is the same programming model that you would get with a blocking endpoint, imperative, synchronous. The only difference is that instead of using a platform thread, you're going to use a virtual one. And so the cost of blocking your thread will be alleviated. The cost of swapping it off and on in order to put it in a wait queue and coming back is going to be alleviated. Basically, performance for free just by using this simple annotation. That's actually the promise of virtual threads. And as you can see, the code is the exact same as you would get on the left with the imperative blocking one.
And just to ask a question here, because I think, why don't we just have a way of saying this is why I want to run everything on virtual thread? Like, why do I have to put the annotation?
Yeah.
Don't answer to that one, Arthur. We will go deep a little bit, and then you say, "Oh, okay, that's why." So let's spot that one. Let's return a uni of answer, and we will provide that answer later in the future, Max.
Got it.
That's my reactive side.
I'll try. Yeah. Sounds good.
So do we actually show some IntelliJ screenshot, or are we just gonna? Is it enough to write those screenshots of endpoints, or do we have to go into the code of the?
I think this is well for me. It's okay. We actually got a question from Sergey. Okay, Sergey it says, "Can you combine run virtual with a uni fortune?"
Yeah, you can.
you can, it means that the subscription on this uni will happen on a virtual thread.
Yeah.
Not sure you will. Not sure it will bring anything because you pay the programming model of reactive non-blocking and you are running on a virtual thread, so you can have the double cost, but you can.
Yeah.
However, one thing that we must probably say is that you might need to put the @blocking annotation too, because by default, what's going to happen is that the Quarkus build engine is going to detect that since your signature uses reactive system terms, so a uni, is going to consider that it's a non-blocking endpoint that will be executed on an event loop. However, we cannot mix event loops and virtual threads. So you will need to put this @blocking annotation in order for Quarkus to understand, all right, I need to run this on a worker thread, so a proper worker thread that is going to return a uni, that's possible, and then put the @run on virtual thread annotation to say, but instead of a traditional worker, I want a virtual worker. And we'll come back on why we can't really mix virtual threads and event loop later on, but it was very, it caused us quite a lot of headaches to figure out because there are some interactions that don't fit very well. So Quarkus doesn't support using an endpoint that runs on an event loop and then offloading some computation to a virtual thread yet, actually.
So, and just which I think is a good question, just so people understand how Loom works. So how does Loom actually work with regular blocking I/O? Can Loom identify a operation is blocking and then suspend pause it?
It's exactly this. So basically, the JDK team have replaced and rewritten a lot of the I/O part of Java, of the JDK, and when you are about to block because you are doing your I/O interaction, it does something very simple. If current thread is virtual, okay, I'm not going to block the current thread. I'm going to just unpark my virtual thread, and my current thread can do something else. So the bookkeeping things that Arthur explained. And if you are not on a virtual thread, well, let's block the thread because there is nothing else we can do. And this code is everywhere in the JDK now, so you rarely have that happening.
And that's the interesting part, that this is the library, so the code that is doing these blocking things has to explicitly says is blocking. That's happening at the that it can be unblocked, basically, right? Or async.
And yes, and well, we will discuss that later, but we don't have the access to the API to do that, so only the code from the JDK can do this and park and unpark your virtual thread.
And that's so this is like, because on thread you have, for example, yield, but this is the same thing, but just only available to the JDK classes. Which limits what framework can do.
Yeah, we will discuss about the current limits probably at the end of this episode. It's not the only one, but it's a big one.
Sure.
And if you want to, have a different, this slide is very much about describing what actually happens with the methods Clement mentioned with park and unpark. So if you need to come back to this slide, we will share with them and feel free to reuse it. But yeah, more than identifying the blocking code, it's more like, your application doesn't have a choice. It will take the path in the JDK that will take, since the entire thing has been rewritten. It's not really identifying, it's just giving a different set of rules to execute your code. So I think this slide is really important because it will describe different ways Quarkus is going to handle the incoming requests. If we, just look at the existing one before we brought the virtual thread support, it's the top one, reactive types of blocking, and the right one, blocking and imperative types. So you had two ways of handling requests before, right? Either you handle it on an event loop, that is the reactive type, and so you could not block it, so you had to use uni, multi, those asynchronous reactive streams types that were going to, interact in an elaborate way in order not to block the event loop, but rather to pass continuations and stuff. Or you could just use a blocking type, and you had a whole bunch of workers. I think by default it was 200 of them in Quarkus. I don't really know the default values, but I think it was something like that. And so, yeah, in this scenario, if you need to block, you block it, and then another worker is going to take the place in order to handle another request. So you had a fixed number of event loops in the first case. The number of CPU cores is the number of event loops you're going to use. And in the other case, you had a limited number of workers that is, you can customize it, but by default, I think it's 200. I don't really know. Now, with the current implementation of Quarkus virtual threads, what you're going to get is a limited number of carrier threads by default. We are using the fork join pool modified version of the JDK team. So it's the default scheduler that will be used to dispatch virtual threads onto carrier threads. So you have a limited number of them by default, and it's elastic then. So if you don't have any more, you don't have any more carriers, it's going to grow in order to keep the same level of parallelism. And it's going to grow until a certain point. I think by default it's 256 carrier threads. That might be wrong. So you have those limited number of good old platform Java threads that are going to be used in order to mount your virtual threads upon. And this number is going to be able to grow until a certain point that you can customize before just say, all right, maybe we're not going to take incoming requests because we don't have enough actual threads to schedule virtual threads on. And so in order to use those different types of scheduling and those different types of handling, you have to play with both the signature of your endpoint and the annotation you can specify to.
So maybe one last thing. So first, one thing you mentioned, but it's very important to understand, is that the default thread pool running your virtual thread, so your thread of carrier thread, is a fork of the fork join. So it's not really a fork join, but it behaves a little bit the same way. As Arthur mentioned, it's elastic, but be aware that when we create a new thread in that thread pool, it's a carrier thread, it's a process thread. So it's 1 megabyte of memory and so on. So if you are running in a container, be very, very careful, or you get killed. So, well, it's up to you, but yeah, it's what happens a lot because you don't understand. You just create millions of virtual threads because you can, and actually it will create more carrier threads because you cannot execute them all, and boom, you reach the memory limits of your pod.
May I ask, so how is that different from today? Like, why would I create million threads, and why wouldn't Quarkus, when a request comes in, create things?
Like it's the same thing. Today, if you want to use all the worker thread of Quarkus, you need to be sure that the memory limits have been set so you can use all the worker threads.
Yeah.
The difference being that if you want to be able to support, let's say your requests take 1 second to process. If you want to support 100 incoming requests per second, you will need 100 threads with a worker model. Now, if you do it with the virtual threads, you will need 100 virtual threads, but maybe those virtual threads will only need 1 carrier thread in order to run. Is it clear? So, you don't have this 1 request equals 1 thread anymore. You have 1 request equals 1 virtual thread that might be and several virtual threads might share the exact same operating system thread underneath. So this mapping is not 1 anymore, it's actually NM. So you're going to have N virtual threads for M carrier threads, and M being lower than N.
Got it.
Do we have a heuristic for what the ratio is, or does it depend completely on the workload?
Yeah, it depends greatly on the workload.
It depends on your code too, and what type of library your code is using, because now Arthur is going to go a little bit on the dark side of Loom.
Yeah. Before we go to the dark side, that's a question here. Any roadmap around Loom on native mode? GraalVM current support Java 11 and 17 is LTS.
I think it's coming in October, in the October release of GraalVM.
Exactly. So the latest GraalVM coming out has the support for Java 19, and it should come there. But we haven't played. I don't think we have had time to play with it yet. But we assume it should just work, and we'll see how.
With a few substitutions and
yeah,
sure, we will make it work.
So for GraalVM supports it in the latest that's coming, or even I think there's even a beta build of it. But and we plan to support it when it arrives. Yeah.
And things we may have less limitations on GraalVM than on the JDK. So actually, GraalVM might be actually a better place to run Loom or virtual thread than the JDK.
Yeah, it'll be interesting. All right, let's go for the doc side.
Yeah, so now that we have given you the promises of our approach, let's see if it actually works, right? And the answer is that it might not work in every case. There is a very known behavior, and the lead, the tech team behind Loom has been very clear about it since the beginning. There are some cases where, unmounting the virtual thread from the carrier thread will not be possible. And it all boils down to having C frames on your stack. We're not going into the details of it. If you're interested, there was a French presentation by Rémi Forax and José Pomar, I think, at Devox, that explained why when you have C stack frames in your stack, you can have specific addresses on the stack that are present, and so you can't move those stack frames around in the memory. And that's pretty much what you do. When you unmount your virtual threads and you put it back on, your stack might not have the same look, and it might not be at the same place. So if you have C frames in it, those frames might be meaningless, right? They might point to completely different locations on the stack. So if you use synchronized lock, under the hood, they use C frames in order to put your lock, basically. If you use native calls, you call native code that's going to call Java code that is going to block. Then you have some C frames somewhere in the stack. That's another example of it. So those examples, you won't be able to unmount your virtual threads from your carrier thread, and what's going to happen is that your carrier thread is going to block. So you're going to be exactly as in the same scenario as before with the normal thread.
So there is a few things to add here. So first, if you don't speak French, which is very unfortunate, but there is this discussion from Remy so the presentation from Remy has also been recorded in English, I think, at Devox UK, but they did it in various places, so you will find it. Here, it's tricky because pinning a carrier thread is as bad as blocking an event loop, because basically you have a very few number of threads, and you are going to block one for an unlimited amount of time. You don't know yet. So what will happen here? So either you constrain the carrier thread pool, so this fork or fork join, to have only a very limited number of threads, and in that case, your code can't make progress anymore, and your whole system will collapse. Or you say, oh yeah, we can grow more and we can use this elasticity, but then you will use more memory, and you may reach the memory limit of your pods or your containers if you are running in such kind of environment. So it's very important to understand that right now, as soon as you use synchronized, as soon as you use native and things like that, you have a high risk to go to that situation. And a promise is a promise, so let's answer to Max now. If you run a CPU-intensive task, you will have exactly the same behavior as pinning. So in the sense that your thread will never yield, will continue executing things because I don't know what you are doing with your CPU, and you are not going to release the carrier thread. So you will have the same behavior here. And that's actually the reason why we didn't want to have run on virtual thread as default right now in 2022, because at the moment, the Java ecosystems and the knowledge of developer is too limited or immature for the ecosystem to be sure that you are avoiding this situation here. Because if you go there and you don't know, well, it will work on your machine and crash your pod. Yeah. So it's probably not what you want.
So is there a distinction? I hadn't realized this before. Is that there's a distinction between normal garden variety threads and the carrier thread, and so the carrier thread is a more precious, unblockable resource.
So carrier is just a functional term, right? It's not actually a different kind of thread. It's just a platform thread that is actually running a virtual thread. It's called a carrier.
Yeah.
But so this behavior will happen in a certain context, and this context being you have a limited number of platform threads on which to dispatch your virtual threads. So it's not a hard limitation as in carrier threads that are different type of threads and you have less of them. It's just those good old platform threads. But since they are supposed to be the place where virtual threads are dispatched, we won't use as many of them as in a traditional blocking way.
And
am I making sense?
That behavior when you go out to native, is that the case with like the newer native programming models like Panama as well?
That's a good question. I don't know. I didn't try that. However, I have tried. So typically, a lot of people say, "Yeah, but nobody's using native in Java." And all the programs I tried are using some way or another some native library, Snappy or something like that.
I just want to. I don't want to oversimplify, but this is the exact same limit as Reactive has, right?
Yes.
The difference there is, and that's why we keep having the different name, is in this case, frameworks can't really affect the situation. It's purely enclosed in the JDK.
Yes,
right?
and actually, since a question from Benjamin, maybe you can post it. So Benjamin is asking if there is a warning message, like when we block a thread in Vertex, and that's a tricky thing. No, there is no warning message. The only thing you can do is to use GFR events, because they emit GFR event when they are pinning a carrier thread, so you can collect them and then look at them. But one, it's only going to do to have pinning, so when we cannot unpack, so that means I operation with C stack or something like this. It won't cover any CPU intensive operations that you do, so that is not going to capture it. So, and that's something that will be developed in the very near future, that we will need a lot more tooling around this concept of virtual thread and pinning of carrier thread, so we can identify these constructs before you reach production. Because that's the problem, that you will never see that on your machine, because you don't. Yeah, it's just fine. You have a very high-speed CPU, and everything is fine, and well, except that it's not.
Yeah, and just to plan a bit the future, the Loom team has stated that although these native calls calling back Java will never be solved, is likely to never be solved. Synchronized blocks might actually be solved, because this is something that is inside the JDK, and by avoiding using native construct in the synchronized block, maybe they will solve the problem. So this is something that they plan not to be a problem in the future. Although in the first release, it is still very much a problem of pinning with the synchronized block.
And well, and about that, imagine the number of Java library out there that are using synchronized notify all. Yes, there is better construct since Java 5, maybe. I can't remember when the lock and conditions have been added. But there is still plenty of libraries that use that, and one of them are JDBC drivers, and we probably are going to see that in the near future. So, Arthur is going to demo that. So it's going to be very problematic until everything works. And when I said GraalVM might be a better place to run virtual threads on the JDK, it's because GraalVM already switched synchronized by runtime rewrite lock, which doesn't have the problem. So maybe you will have less pinning on the with native image.
Yeah, maybe I missed that before, but that's did you mention that problem that synchronize is not good in Loom?
Synchronized is definitely not good in Loom as of today. They have work in progress to actually rewrite it using rewrite lock. It's hard to do. It's not that simple, but yeah, I know that there is work in progress. But the second thing, which is the native stacks, no, that is never going to be fixed.
Yeah. But just to make sure we're not giving people the wrong impression, the team has been very clear since the beginning of the project, right? It's not something we are just discovering as Loom is released. We've known it for years, and they always have been very clear on synchronized will likely be an issue for the first release.
Yeah.
So and synchronize and
I think I just want to because this is one thing I until you guys actually sat down and handhold me through the explanation. My understanding of Loom, like let's say a year ago or 2 years ago, was, hey, this is going to be very transparent for the users to do, etc., etc.
And well, that was very good marketing.
No, wait, no, I want to be like I want to be very honest here. Like that is true if all the libraries that are using has kind of adjusted to the reality that Loom expects, which is it has control over the scheduling completely. It has there's no synchronize in your call because then things go all haywire.
Be careful with thread locals, or you have a performance penalty.
And these are all things that we should work. Like if you look at code over the last 10, 20 years in Java, all these has been minimized, right? But there are still traces left, and that's why we are a bit. So that's the dark side of this thing, right? The thing is, there are ways to fix this and improve this. It will just take some time to get there. There was a question here actually that is Loom meant to replace Mutiny, or will it be integrated?
It's going to be integrated. Actually, when I started Mutiny, Loom was starting. The project Loom was starting. It already started, and I worked a specific group, which is named Await, to be sure that we don't block the carrier thread. So basically, if you have an asynchronous operation, you can say, "Hey, I'm going to await for the results, and this await is not going to block the carrier thread, and we guarantee that." So we are going to see this with code, but basically, it's already integrated like this. Once everything, the whole Java ecosystem will switch to Loom, and we'll have the performance we have right now with Loom compliant code, maybe Mutiny will change. Well, the shape of Mutiny will change. Mutiny will still be useful for streams, but less for single asynchronous operation. Yeah. But right now, it's aimed to be integrated.
Yeah, and what I'm trying to get to is like the way I see this is that there's the traditional imperative, there's the reactive where Mutiny is, and then there's Loom. It's like the 2D, like it's the 1.5 version. It's somewhere in between. And I think for a long while we will have all three approaches in Java. And depending on how fast we find ways to deal with Netty not being fully Loom compliant and Loom compliant not being fully Java ecosystem compliant, this will vary. So I think it's important to realize that these are probably three models that's going to be in Java for a while.
Yeah, probably, and at least 5. At least 5 years. It's going to take some time to re-implement most of the library we use, like GDBC, Hibernate, and things like that.
So with the imperative model, you're not going to have bugs, but it's going to be slow. Yeah, right. With the reactive model, you're going to have bugs, and they're going to be your fault because you're too stupid to understand reactive.
Yeah, but you will be very fast.
You're going to have bugs, but the good news is they're not your fault, and there's nothing you can do to fix them because they're in their underlying libraries.
That's a good summary. Yes.
If you'd like any other good news, please just feel free to ask.
with a tongue cheek. And here's actually one that I like. Benjamin asked: is there work on Open Rewrite or something like that to help migration to Loom? So this I want to be very careful on. There's no way that you can migrate reactive to Loom or Loom to the thing is the existing imperative code will be Loom compatible. Like the syntax of the code, you can't decide if it's wrong or not. You'll have to log into synchronize and lock, which will be very hard. Another one is like, oh, you already have Mutiny code. How do I get it to Loom? Those are like two different programming approaches, or so. I just don't try to do this.
The later is actually simpler in the sense that you just do await at most on all your calls and you're good. But I don't believe it can be automated.
Yeah, and also this is the thing. People like again, great for the marketing team or not marketing team, but the marketing around Loom has been like, hey, this will just automatically work. Like this is still concurrent programming, right? That problem doesn't go away when you use virtual threads. Like you still have to coordinate how you access stuff. So yeah, it's tricky. Okay, we have like 10 minutes left. What do you want to get to?
Also, maybe you can show some code and explain where it's spinning and how
Yeah.
we work around it in Netty, and I will conclude with our stance around Netty and Loom.
Sure. We also have fancy graphs in the slides if you want to check them out later. So I'm just going to share another another window, which is my IntelliJ editor. Maybe I need to go to
It is
presentation.
Bigger fonts.
Yeah. Should do the trick.
Yes, that's good.
Okay. So this is basically, the screenshot we've showed you earlier about the different ways to implement the same thing is extracted from this code. So we have the reactive one, where you are going to use those fancy declarative map stuff and uni types. You have then the blocking one, which is above, where you don't use any of that fancy stuff. You just block until you get the results, and then you return one from the list. And then you have the Loom stuff. And so here we implemented it using two different DB drivers. We have first Loom JDBC, which is going to use the Postgres JDBC driver. I think it's version 40.5. It's the latest one, so it's 42.5 or something. Don't know the versions on the top of my head. That is going to use the findful blocking operation, which is the exact same one as the blocking code. And then we have Loom using the Vertex Postgres reactive driver. And so this is what Clement was telling you about the await operation, right? We have async functions that go with Mutiny Vertex, and we have the async and await variants that are going to be used in order to await for a result without actually pinning the virtual thread to the carrier thread. And the way we know that the thread is being pinned is very simple. When you go to the actual definition of the method, you have this prepare statement.execute query. This is a Postgres driver code. And when you go into this method, you see that in the implementation, I think it's this one. Yes, everything happens inside the synchronized block. So you see you're 2 clicks away in the editor to see why actually the request is going to pin the virtual thread to the carrier thread is that when you execute a DB request on a virtual thread using the JDBC driver, you're going to enter this synchronized block, and you're going to execute your query within the synchronized block, which means that during the entire length of the query, your virtual thread is going to pin your carrier thread that is going to be blocked.
So if you do a query that takes 2 minutes, for example, you are going to pin the carrier thread for 2 minutes.
Exactly.
So that's the important thing. And even if we fix that synchronized, there are other issues. And I've tried, I don't know how many databases, but a few of them, and most of them, if not 90% of them, have one way or another are pinning the carrier thread.
Yeah. And I'll put on the OpenJDK hat here, saying this is not a problem. Well, sorry, this can be fixed.
Exactly.
This one can be fixed,
right?
Yes.
So that's the challenge.
There are some drivers that use native code. These ones cannot be fixed.
Yeah, and that means that if you're using, I don't know, native driver or something, you will, your framework code will have to know how to get off the pin carrier threads somehow.
Yeah. Offload to a regular process thread and things like this.
Yeah, exactly.
There's another interesting one here from Rohit. Will there be any significant performance difference between reactive model and virtual thread model?
Yeah, those are the fancy graphs we were talking about earlier.
Yeah, so maybe you can go quickly to this graph just to explain them, because basically we have seen that, so a lot of parts will need to be implemented or changed. Just while you are looking for the charts, a few things. So right now the Loom integration in Quarkus is limited to REST-easy reactive, and it works with Hibernate reactive too. So you can use that. You cannot use Hibernate Classic because of the JDBC dependency, which is pinning the carrier thread. But REST reactive and Hibernate reactive can be used with our R2 non-virtual thread. And when you use Hibernate reactive, you just do a wait at most, and you put your deadlines, and boom, you're done. So that's the good news. Things like Kafka are very, 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 very challenging. Right now, I don't have a good solution to do that, but we're working on that. So extending increasing the size of the ecosystem that will support this run on virtual thread.
Yeah.
So yeah, also we'll show you some of the graph we did.
So there is actually an academic paper in the pipes, but it's been refused the first time because I'm a terrible writer. But actually the experimental protocol appears to be sound. So the way we've done those measurements appears to be sound and well, quite okay actually. And so the results are those ones. What you can see is that in red you have the response time and the throughput of your system using the reactive model. So on the left-hand side, you have the response time. So that's more the latency, that was better. On the right, it's throughput, so higher is better. So red is the reactive model, dark blue is virtual thread Quarkus, and light blue is the good old blocking Quarkus. So as you can see, in terms of latency, blocking you will have your latency going through the roof very early, around 1,000 requests per second. We're not detailing the actual system we run those tests on, but it's all in the slides if you want to check it out later. With virtual threads, it's going to go through the roof a bit later, around 1,200 requests. And for reactive, it's going to be 1,500 requests. So basically, those are when your system will become unreliable and will likely drop packets or even just crash under the load.
But this is a moment in time situation, right? That's given the current libraries and the current how they work, right?
Exactly.
And there's no we believe that over time the Loom one will get better. And I think, well, tell me if I'm wrong here. The way I see it is Loom will probably get to a level where for most use cases it will be performant. And it will have the advantage that it's much easier to understand because it's imperative and less easier to debug. But there will still be use cases for a pure reactive model where the use cases where you're processing streams and it will just be able to do it more efficiently than Loom ever can do.
That depends on your target concurrency level. If you are building a gateway or stream systems, reactive will still be better. There is no you can't compete. However, and I'm the first to say that 90% of the case are different. More than 90% of the case, probably 95. Yeah, I can't do more than this, but yeah, 95% of the case don't need that level of concurrency, and Loom will be a perfect for them because it will bring good enough concurrency level for you.
Yeah. So the way to think about it is that if you want this kind of concurrency today, reactive is the way to go. Loom will probably take over a lot of that kind of workload, but we're not talking tomorrow. We're talking years out. And if you do try Loom, you just have to be aware of these limitations. Like, for example, the one thing that I think Loom the fact that Loom can't be used with JWC massively limits the thing. I'm be clear. Loom today can't be used with JWC. Is a limit, right? It will be hopefully fixed in a amount of time, but it's gonna take some time. So,
And just one important thing: those graphs are not virtual threads versus Quarkus reactive. It's Quarkus virtual threads. So the integration of virtual threads within Quarkus versus the integration of reactive model within Quarkus. So we're not comparing a framework built around the idea of virtual threads with Quarkus built around the idea of reactive programming, right? The main idea that comes from these numbers is that integrating virtual threads inside of Quarkus seems to be better than using good old blocking model, but won't get to the point. You won't get the performance as good as Quarkus reactive, since Quarkus has been built around the idea of a reactive model. So this is not really an idea of how virtual threads will behave in the Java ecosystem, but how they behave within the Quarkus of Quarkus, right? So
well,
those are very different.
And that's probably, yeah, I will conclude on that. So I sent an email to the Loom mailing list in July, explaining our experiments, what we are seeing, and the journeys we had, and what we would like to have. So right now, Quarkus is based on Netty. So the whole network stack goes through Netty, and Netty is a very mature, efficient, performance, very large network stack. However, Netty wants to schedule his own event loops, and we didn't discuss that, but virtual thread and carrier thread cannot be event loops because right now, Loom, well, the Loom API does not give us access to what we need, so customizing the scheduler. So changing their fork join and doing something different. So it has been discussed, it's on the roadmap, but we don't have any ATA yet. So right now we are like this. The other approach is to implement a full network stack with Loom in mind, with virtual thread in mind, and we build everything with that in mind. While it looks exciting and things like that, this is going to take years for very, very skilled engineers to reach the maturity of Netty doing that. Because you can do HTTP 1, 2, okay, fine. But network is a lot more than HTTP, and you will have to play with things like, oh yeah, I need DNS. Oh yes, I need UDP. Oh, I need HTTP 3 with this mixed things. Oh, I need my messaging protocol. I need MQ. I need Kafka. And every time you will need to rethink and these protocols and see how you are going to map them on the idea of virtual thread and things like that. It's a massive amount of work. Actually, seriously, my evil me is telling me that would be great work and you should start right now. But my more let's say Cartesian side say, yeah, well, okay, are you going? You want to have a life in the next 5 years, so probably not great to start such kind of marathon.
So, and you see, there's this product announced today called NEMA that is by the Hill and folks, which are using this approach of re-implementing things, and it looks super interesting, and we'll keep an eye on it. But this is the thing, again, my understanding of this early on was like, hey, this is how it will happen, and I'm probably sure it will happen. It'll just take longer than I think people expect. The thing is that Netty, for example, one of the reasons why we can pull out so high performance or users is some of the stuff Netty does, like the IO, what's called IO U-ring, and other integrations are just like unbeatable. And those right now, because of how Netty works and how Loom is, let's call it enclosed, makes it hard to get those to play together. But it's gonna be interesting to see what we can do. Yeah.
And don't forget that, well, at least for Quarkus, we actually really centric on this idea of containers and running in very low environment in terms of resources. Or you are very, very rich, so it depends. So we need to keep that in mind, that our amount of resources is limited in terms of CPU, in terms of memory. Holly can talk about that also in terms of energies. So we need to work well, be reliable, fast on this platform, on this environment. And Netty works very, very well on that side of the spectrum. Yeah, of course, if you have a mainframe, yeah, but if you have a mainframe, you can afford having 10,000 worker threads. That's not a problem.
Okay. Anything else you want to add?
No, well, we have a lot more details on this, but we didn't want to spend the full afternoon with you. So stay tuned. Arthur is working on that. He's also doing some more academic work too. Not a PhD, but yeah, we will continue working on this. Native is definitely something we want to try as soon as we have that access to that version of GraalVM. And yeah, we will continue working on this. The ecosystem will evolve, so the limits we have today won't be the same tomorrow. So be very, very careful with this. However, before going with Loom, I really recommend you to use GFR events, collect them, look at them, because something that looks to work on your machine may be a disaster in production if you are pinning too much carrier thread one reason or another. There are even reflection calls that can pin the carrier thread. So there is situations that are very hard, even for a skilled engineer to detect. So yeah, go there, observe, collect, analyze, and then go with that. But yeah, don't rush it.
Yeah,
it's a big changer, but yeah.
I see it as well. I want to leave it. This is that we are very positive on Loom, on the program model and what it enables. It's just how we get from here, from where we are now, to that new world. It requires more work than it's not something that OpenDK team can handle on their own.
Yeah.
It requires the whole ecosystem. And what we are suggesting, and this is what is in the email Clement talked about, is that they open up a little bit so that we can actually fit in. And we don't say Quarkus, but Spring, Micronauts, all of them, right? Yeah, so it's going to be interesting. Definitely try it out, for sure.
A guide will be published very, very soon, because right now it was not really documented. We wanted to continue doing experiments, but a guide will be released probably this week, something like that. Arthur is on the pull request. I received the notification. I need to review it. So basically, we are at that stage. So the bottleneck is me.
And that's on using Quarkus with virtual threads.
Yes.
So.
Oh, and with we have the dev mode working. So the rest is already there, but you just need to be careful.
Yeah. Cool. All good. Then I'll call you for today. We don't have more questions, I think. So good. Well, see you guys next week.